All right, so day 2 of related rates. It says, what is the sphere's surface area when the volume increases twice as fast as its radius? Okay. What is a sphere's surface area? So I want just surface area, not the rate of change of the surface area. I just want the surface area. Surface area formula. When the volume increases, so that's dV dt, change in the volume, twice as fast as the radius is increasing. Just kind of have that relationship. Okay, so I want surface area, so the surface area formula is going to be on the main stage. But here's the question, and this is why I love these problems. You can't just robotically go take the derivative of the surface area formula. I don't want the rate of change of the surface area. I wasn't given that, and I don't want it. So there's no need to go take the derivative of the surface area formula. Now, I was given a relationship between dV dt and dr dt, and dV dt is the change in the volume. So what I'm going to do is I'm going to take a volume formula, I'm going to take the derivative of it and go from there. So dV dt equals 4 pi r squared dr dt. Really important that you understand the thought process behind that, because this is not just robotic math. This is understand what you want, think about what you're given, what are you trying to find, and what's the best path to get there. Let's see. I know I don't have dV dt, and I don't have dr dt, and I don't have r. So I don't have any of these variables that are in this formula. But I know that dV dt equals 2 dr dt. So I'm going to replace this with that, like substitution. So 2 dr dt, because my dr dt's will divide and cancel. So they are going to, if I divide both sides, they're going to cancel. So now I can solve for r. So I'm going to divide by 4 pi, so 2 over 4 pi, which is 1 over 2 pi. So r equals the square root of 1 over 2 pi. Well, the square root of 1 is 1, so I could write this as that. So now I know r. I never found dr dt, and I never found what dV dt is, but I know r. All right, well, let's think about what I wanted. I wanted SA, I wanted surface area. Well, to get surface area, all I do is I need to know r. So now I can take surface area, 4 pi r squared, and I can plug my r, and either one is fine. I'm partial to that one because I have an issue leaving 1 under the square root. It's going to get squared. Square root of, or the square of a square root just gives you what's inside. Pi's are going to cancel. 2. Now this is surface area, and it didn't say if it was inches or feet or miles or whatever, so we're just going to say units. It is surface area, so it's going to be units squared because it's an area. Great problem, because it's not a cookie cutter kind of problem. Like, you're given a relationship and you're asked for something that's not a rate of change, but you're given information about a rate of change. It's like a puzzle. A circular puddle of oil is growing on a garage floor at a rate of 20 centimeters squared per day. How fast is the radius of the puddle changing when the radius is 10 centimeters? How fast is the diameter of the puddle changing? Okay, so we have two parts. I'm going to label part A, part B. So let's talk about what we have. Circular puddle of oil is growing, so that's volume. No, that's area. It's not three-dimensional. Sorry. It's a puddle. So dA dt, change in the area, is 20 centimeters squared per day. Okay, so part A wants how fast is the radius of the puddle, so dr dt, when the radius is 10 centimeters. Okay, so I want dr dt. I was given dA dt, so let's use a formula that uses area. Well, this is a circle, and area equals pi r squared. So tell you what, pause me and go try this problem, and then hit play and check your work. So dA dt equals 2 pi r dr dt, and dA dt is 20, r is 10. I'm looking for dr dt. That's going to be 20, so it's going to be 20 divided by 20 pi, so 1 over pi equals dr dt, and I'm going to put units of measurement. This is radius, so that's a linear measurement, so this is centimeters per day. So there is part A. Now part B says, how fast is the diameter? Okay. Well, a couple different ways you can do this. You can put area in terms of the diameter instead of radius. I'm just going to write a relationship between diameter and radius. So I'm going to kind of avoid the whole area thing. I know that the diameter is twice the radius. I want how fast is the diameter changing. dd dt when r is the same 10, and that's not super clear, but that's what they want when r is still 10 centimeters. So I can dd dt, derivative of that would be 2 dr dt. Well, I now know dr dt. So dd dt equals 2 times 1 over pi, which is 2 over pi. Diameter is also a linear measurement, centimeters per day. And doesn't it make sense that the diameter is changing twice as fast as the radius is, because the diameter is twice the radius? And so it's just 2 times that answer. All right. So in the last video, we talked about right triangles. And it was really based on, or everything we could, that we needed was the Pythagorean theorem. And I alluded to the fact that we could use right triangle trig if angles were involved, but we didn't have any angles on day one because we were in the shallow end of the pool. We are now in the deep end of the pool. So now we're going to talk about angles, which means we're going to talk about trig. It says the television camera at ground level is filming the liftoff of a rocket that's rising vertically. According to the position equation, S equals 50t squared, where S is measured in feet and T is measured in seconds. The camera is 2,000 feet from the launch pad. Find the rate of change in the angle of elevation of the camera shown at 10 seconds after liftoff. So I want the rate of change of the angle. So d theta dt when t equals 10 seconds. All right. Let's see. I am referencing that angle. I've got a position equation for S for the rocket, so that's the opposite side, and I know the camera is 2,000 feet away from the launch pad, and that is a constant, so that's very nice. So this is opposite and adjacent, so I'm going tangent. So let's see. Tangent of theta equals S over 2,000. That's T, oh, hold on. TOA, T-O-A. Okay, so I'm about to take the derivative. So I'm going to look at this S over 2,000 as a 1 over 2,000 S. Because, again, I'm about to take the derivative, and I don't want to look at that and think it's a quotient rule. I kind of want to pull the S and the coefficient separate. Just makes it easier. Okay. Derivative of tangent is secant squared. And then I have to take the derivative of the inside, which is a theta, and I'm taking the derivative with respect to time, so that's implicit. There we go. Derivative of the right-hand side is just going to be the 1 over 2,000, and again, implicit. Okay, I am wanting this guy. Oh, that's not what I wanted to do. I want this guy. So I need theta, and I need ds dt. Let's go find ds dt first. Now they gave me a formula that was s equals 50t squared. So I can take that formula and take the derivative, and that will produce a ds dt. So ds dt equals power rule 100t. Now, I just about wrote dt dt. But let's think about this for a second. I'm taking the derivative of t, of time, with respect to time. So this side doesn't need implicit because that's the variable I'm taking the derivative with respect to. So here's the one time you don't have to implicit because that's a t. Okay. So let's see. I know. What do I know? I know. Okay, so I'm going to put that in here. So, and I'm also, no, not yet. I'm going to do one thing at a time. Try not to blow your minds. Okay, so I can do a little cleaning up, and also to solve for d theta dt, I'm going to divide by secant squared, which is going to put secant squared on the bottom, which means I'm going to kick it up as a cosine squared on the top, because you guys know that 1 over secant is cosine. D theta dt. Okay, so again, I'm dividing by secant squared, so that's going to make that cosine squared theta. And then I can reduce the 100 and the 1 over 2,000 to a 1 over 20 t. Okay, all right, not bad. Now let's see. I've taken the derivative, so I can now start finding some things. The t in question is at 10 seconds. So I am going to plug a 10 in for him. I need to go find him. Okay. So t is 10. Yeah, and I need to go find I need to go find theta or cosine squared of theta, either one. But something needs to go here. The t is easy because it's 10. They told me that. All right, so let's go back to our right triangle where this was 2,000, this was S, and this is theta. Now it tells me that S equals, where'd that formula go? 50t squared. So if I know t is, what is t? T is 10. So 10 squared is 100. 100 times 50, 100 squared is, oh, God bless. Let's try this again. T is 10. 10 squared is 100. 100 times 50, it's 5,000. Sorry, distracted. Okay, S is 5,000. So now I can find cosine of theta. And again, I want cosine. Cosine is CAH. So adjacent over hypotenuse. Well, hypotenuse, so I can just Pythagorean my way out of that. So 2,000 squared plus 5,000 squared equals, I don't know, call him X. X squared. And if I grab my handy dandy calculator and type that in, ooh, that's big, and then I square root it. Ooh, that's not pretty. Okay, so I'm going to leave it as the square root of 29, 1, 2, 3, 4, 5, 6. I think 1, 2, 3. Yeah, if my eyes are right. And I tried square rooting and it gave me decimals, and I really don't want to go decimals until the very, very end. Okay, so I now know that that is the hypotenuse. So now I need cosine of the angle. Okay, now again, to get cosine of the angle, I don't have to know what the angle is, but I know that cosine of the angle is adjacent over hypotenuse. So d theta dt, remember this is CAH, and it's squared. So adjacent over times 1 over 20 times 10. Ooh, look at us. Here we go. Oh, if I square that, that's big. And then if I square the square root, now look at this. That's 4 over 29 times a half. So d theta dt, the 1/2 and the 4, 2 over 29. Look how pretty that is. That is nice. Okay, so again, I never found theta. I don't need theta. I need cosine of theta. So I did a little right triangle trig, and I found my third side of my right triangle, my hypotenuse, by using the Pythagorean theorem. I left it under the square root because when I square rooted it, I got a decimal, and I don't want to go decimal until the end. And plugged in adjacent over hypotenuse, and then squared it because the cosine is squared, and then cleaned, and it cleaned so pretty. Now this is theta. So this is an angle. So this is radians per, I think it's seconds. That is a great deep end of the pool problem. So might be worth pausing, going back and just watching that problem again without having to write it down, and just kind of marinate on it a little bit, let it soak in. Corn is poured through a chute at the rate of 10 feet cubed per minute, so we're talking volume, and falls in a conical pile. So think of an ice cream cone upside down, conical pile, or a caution cone, like a parking cone, whose bottom radius is always half the height. Okay, that sounds like a relationship. How fast is the radius of the base changing when the pile is 8 feet high? Oh, there's another question. How fast will the circumference of the base change when the pile is 8 feet high? Okay. So let's see. They are telling me that dV dt equals 10 feet cubed per minute. R is radius. No. Oh, R is 1/2 the height. Sorry. Whose bottom radius is always half the height. Okay. How fast is the radius of the base changing when the pile is 8 feet high? So when height is 8 feet, I want how fast will the radius change? dr dt. Okay, so this is a cone, and they didn't give you the volume formula, and we'll worry about memorizing these kinds of formulas as we prepare for the exam. So any of these obscure cone or sphere volume area formulas, I'll provide those for you. I expect you to know circle stuff, area of circle and circumference. But all these other ones for now, I will provide them for you because we're focusing on how to use them. Okay. So volume of a cone is 1/3 pi r squared, h. Okay, now here's the thing. I have two variables. I have an r and an h. So if I go take the derivative right now, I'm going to have a product rule. I'm going to have a dr dt, which is great because that's what I want. I'm going to have a dv dt, which is fine because they gave it to me. But I'm also going to have a dh dt, which I don't have and I don't want. So before I just blindly dive in and start taking the derivative, I'm going to use the relationship that they gave me to put this equation completely in terms of r's because I want a dr dt. Okay? So I am going to take this formula. I want to replace h. So I'm going to solve this guy for h. So h equals 2r. So if that becomes a 2r, this formula becomes 2/3 pi r cubed. Make sure you're okay with that. Now I can take the derivative, and it's not a product rule, and I have no dh's, dt's, because I have no h's anymore. All right, so here I go. dv dt, pull the 3 down, 2 pi r squared dr dt. Okay. dv dt they gave me, that was 10. 2 pi. Now they didn't give me r, but I need an r. But they did give me an h. H is 8. Now I can use the relationship that r equals half of h to know that if h is 8, then r is 4. So this is going to be 4 squared, which is 16. And that is who I want. So 10 equals 32 pi dr dt. Divide by 32, and I can reduce that. 5/16 pi dr dt, I need units of measurement. This is radius, that's a linear measurement, so this is feet per minute. So just another great problem where you're using this sort of side noted relationship between R and H and being super smart about what's coming if you take the derivative and to know to plug the H in and replace it in terms of R. It's very smart math, very smart calculus, thinking, it's thinking. Okay. Second question, how fast will the circumference change? Okay, so now I want dc dt when h equals 8 feet. Okay, so I need a formula for circumference. Circumference is 2 pi r, which you are expected to know. That's only r and only c, so I don't think I need to replace anything. So I'm going to go ahead and dc dt 2 pi dr dt, and I found dr dt, so dc dt equals 2 pi times 5 over 16 pi. Pi's are going to cancel, and the 2 and the 16 is 8, so 5/8. Circumference is a linear measurement, so this is also in feet per minute. Beautiful. The shadow problem. All right, so I think the next two are shadow problems. Light on the ground 50 feet from the wall shines on a 5-foot tall man walking to the wall at 2 feet per second. At what rate is his shadow decreasing when he is 10 feet from the wall? Oh, that's just awesome. Okay, let's do that again. Light on the ground 50 feet from a wall. So here we go. 50 feet. And here's a light. And it shines down on a little man who is 5 feet tall. So the light shines on him and makes a shadow. All right, let's see. Light on the wall, 50 feet, shines on a 5-foot tall man walking to the wall at 2 feet per second. Okay, so this is the wall. And light on the ground. Here's the light. There's the light. The light's on the ground 50 feet from the wall. Okay, sorry. I thought the light was on the wall. No, light's on the ground. Light on the ground 50 feet from a wall shines on a 5-foot tall man. Okay, so where is his shadow going to be? His shadow is going to be here on the wall. So we'll call that Y. Shadow's not on the ground because the light is shining like behind him. So it's going to project his shadow onto the wall. I'm going to call this distance X, and you'll see why here in a second. It says that the man is walking towards the wall at 2 feet per second. So this distance right here is increasing 2 feet per second. Now, some people will say, well, I want this to be X. Okay, so if that's the case and he's walking towards the wall, then that distance is getting smaller. So that would have to be negative 2 feet per second. But I'm going to put my X on the outside. Okay, I want, at what rate is his shadow decreasing? So as he walks closer to the wall, I want the rate at which his shadow is decreasing when he's 10 feet from the wall. Okay, so when this distance here is 10 feet, but it's not always 10 feet. Like, that's not a constant. And I really don't want another variable. So what I'm going to do is I'm going to use a relationship between the fact that I know that this is 50 and I know that this is x. So what's left, what's blue, is going to be 50 minus x. So I want the 50 minus x to be 10. All right, pause for just a second. Make sure your brain's wrapped around that. 50 is the whole distance. I want to know when this is 10. Well, this is x. So, okay, so you could do x plus 10 equals 50 and add the two smaller parts to get the whole if you wanted to. And then I just solved for 10, so subtract x over. Either way you want to look at it is fine. I see the whole minus the piece to give me the 10 that I want. But you could look at it as the two pieces added together to give you the 50. Whatever floats your boat. But the point is, x is going to be 40. But that doesn't come into play until after the derivative because that 10 is not a constant, so it can't go in early. Okay. I have no formulas here. I mean, I can go Pythagorean, but because these are right triangles, in fact, there are two of them. There's a little one and then there's the big one. But I don't care about the hypotenuse. Like, that's not what I'm interested in. What I'm going to do is I'm going to look at ratios of triangles. So I'm going to look at, well, that gets covered up. I'm going to look at green. I'm going to look at the big triangle. And I'm going to compare it to that little triangle. They're both right triangles, and one is inside the other. So that means their corresponding parts are in proportion to each other. So like the backbone of the big triangle, which is y, is to the backbone of the little triangle, which is 5. So here's what I'm saying. Y is to 5. So big backbone is to little backbone as, all right, now let's do big bottom. 50 is to little bottom, x. So backbone of the big triangle to backbone of the little triangle equals bottom of the big triangle over bottom of the little triangle. So it's a proportion, it's a ratio. So now I'm gonna cross multiply. And I want dy dt, so I'm gonna solve for y. And I'm not gonna divide by x, I'm gonna write 250x to the negative 1. Because I'm going to take the derivative, and I don't want the x in the bottom because I don't want to have to do a low d high. So now I have this relationship. So now I'm going to take the derivative, dy dt, which is good because, again, that's what I want. And that's why it's so important to write that, because you can get so bogged down in this. You're like, well, I don't even know. I don't even know what I'm looking for anymore. So it's very important to write that down from the beginning before you kind of get knee deep into this problem. Let's see, negative 250x to the negative 2 dx dt. All right, looking for dy dt. I need x, and I found x to be 40. And that can go in now because we are post-derivative. And now I need dx dt, which they gave me. So this is negative 500 if I multiply the 250 and the 2, the negative 250 and the 2, and then 40 squared and move to the bottom is going to be a 1600 on the bottom, and then those cancel. So negative 5/16, and this is feet per second. Now that is negative because his shadow is going to be getting shorter on the wall. That distance is going to be decreasing. Great problem using proportions of a small triangle sitting inside a big triangle. And just to point something out, when you do this triangle, you could have done big backbone over big bottom and had a fraction, a ratio that has your big triangle in it, and then little backbone over little bottom. Because when you cross multiply, you still get the same. So I did a backbone ratio and a bottom ratio. This is a big triangle ratio to a little triangle ratio. Either way, however you want to organize your information, you'll still get the same equation. Okay. A 2-meter tall man strolls at 1 meter per second past a streetlight that is 5 meters tall. He notices that his shadow is moving pretty fast. How fast is the tip of his shadow moving when he is 8 meters away from the light post? How fast is the length of his shadow increasing? Okay, so two very different questions. How fast is the tip of his shadow moving, and how fast is the length of his shadow increasing? Okay, so we have a street light that is 5 meters tall, and I have a man who is 2 meters tall. And, oh, why does it do that? Just to get my triangle. Let's see. He's strolling. Where is he strolling? Past a street light. So he's headed in this direction. Well, I'm going to let that be y and that be x. Now the man is strolling 1 meter per second. So that's the rate of change of x. So dx dt equals 1 meter per second. How fast is the tip of his shadow moving? Okay, so I want dy dt when x equals 8. Okay, that's not bad. So let's get a ratio here. I'm going to go big over big. So big back over big bottom. Now go little triangle. Little back over, okay, so now I don't have, let me highlight it so y'all can see it. I don't have this guy. Well, that guy would be y minus x. Big part minus the other part is going to give me the yellow part. Okay, so I did big backbone over big bottom equals little backbone over little bottom. The x is not a piece of a right triangle. Like, it's not a whole piece of the right triangle. So there's no plain old x here. I'm going to cross multiply. I want y, so I'm going to solve for y. So let's see, I'm going to subtract the 5y over. So negative 5x equals negative 3y, and then solve for y, so y equals 5/3 x. Now I'm going to take the derivative. dy dt equals 5/3 dx dt. and they told me that dx dt is 1. So dy dt equals not 53, 5/3. Technically, it's times 1. I'm going to show my work. Dy dt equals 5/3 meters per second. That's the tip of a shadow. That is the length of y and the rate at which it is changing. Now, the next part says, I want the length of a shadow. Well, the shadow is that yellow highlighted part. So the length of shadow is y minus x. Big part minus the part I don't want leaves me with the part I do want. So the length of shadow is y minus x. So I want the derivative of that. So I want d y minus x over dt. Ooh, let's stop for just a second. Let's soak that in. The length of the shadow is y minus x. Well, I want the rate of change of the shadow. And the shadow is y minus x. So I want d y minus x over dt. Fun fact about this, it's the same thing as dy dt minus dx dt, which I know both of. He's 5/3. And what was dx dt? Dx dt was 1, which will be 3/3, so 2/3 meters per second. dy minus x dt. Make sure you understand why the length of the shadow is y minus x. All right. Okay. So a tank of water in the shape of a cone is leaking water at a constant rate. Okay. Gonna need a cone for this one. Here we go. Is leaking water at a constant rate of 2 feet cubed per hour. That is volume. dV dt equals negative, because it's leaking, feet cubed per hour. The base radius of the tank is 5 feet. And the height of the tank is 14 feet. Now that's of the tank. So I guess this is upside down. But that's not of the water in the tank. That is of the tank itself. So this is 5 and this is 14. But there's a water level in here that has a different radius and a different height. However, you can see that now we have a triangle within a triangle. So we are going to use some ratios here. At what rate is the depth, that's height, of the water changing? So I want dH dt when h equals 6 feet. So when the height of the water is 6 feet, at what rate is the depth of the water changing? And again, should be negative because we are decreasing. Okay, so let's start with the volume formula. Volume of a cone, which again I would provide for you, is 1/3 pi r squared h. I have two variables here, and that bothers me. But I want dH dt, and I was given h, so it seems like I don't want the r's for this problem. So I'm going to take this whole right triangle, similar triangle ratio proportion stuff, and my goal is to replace him because I want dH dt. Okay, so let's see. Big to big equals little to little. And I have to use R and H because the water radius and the water height, it changes. The 5 and the 14 is of the tank. That never changes. So now I'm going to cross multiply.
And I'm trying to replace r, so I'm going to solve for r. Now I'm going to go replace. And then I'm going to clean 1/3 pi, that's 25. 14 squared is 196. And I'm going to keep cleaning. 196 times 3 is 588. Pi h cubed. Okay, I've done no calculus yet. I've done some proportional triangles and a volume formula and some algebra. That's it. Okay, so now I'm going to pull the trigger and take the derivative. Let's see, bring a 3 down, that'd be a 75, but it does reduce. 588 will reduce with the 3 that I bring down. That gives me 25 over 196. So I'm bringing the 3 down, but the 3 reduces with the 588 to give me 196. So instead of writing 75 over 588, I'm going to go ahead and reduce because it makes life simpler. And on a problem like this, we want as simple as we can get. All right, I was told that dv dt was -2. I need h, and I want dh dt. Oh, they told me h. H was 6. So -2 equals 6 squared is 36. So then when I multiply this by 36, I can still reduce a little bit. So I'm on my calculator, guys, I'm just doing 36 times 25 divided by 196 and then math fraction. And it cleans it up very nicely for me. Okay, so make sure you're comfortable with that. I got 225 over 49 pi bhdt, and then I'm gonna divide, which means I'm gonna Bojangles 225, and that's gonna give me, and the pi is gonna be on the bottom. So when I multiply that, it's gonna give me -98 over 225 pi dh/dt, and this is feet per hour because it's a height and it's negative, which makes sense. All right, some good algebra in that one. Okay, now it says at what rate is the radius of the top of the water in the tank changing when the depth is 6? Okay, I'm not going to go back to my volume formula. I'm going to stick right here. Well, I'm going to stick right here. So if R equals 5 over 14H, I'm going to take the derivative because I want dr dt. Well, this is fun. But I know 5 goes into 225, and I'm pretty sure I can reduce the 14 and the 98. Feel free to just type that into your calculator. Leave the pi out of it and just have a pi in your answer on the bottom. And mine reduces to a -7 over 45. And this is feet per hour because it's also a linear measurement. Good stuff. I told you today was deep into the pool kind of stuff. These are tough. These, I 100% agree. These are tough because it's not a super clear path as to what you should do right off the bat. And the triangle problems with the shadow and labeling who's x and the y minus x and all that stuff, like that's tough too. So if you have questions, please come see me or ask me at the beginning of next class, and I'll be happy to say them 1,000 different ways until it makes sense, until it lands. But really the way to make sure that you're good with these is to just practice, which is what your homework is for.